Now that we've learned about an installations of any impulse turbines, and now let's start and move on to the velocity triangle of an impulse turbine. Let's take a look at an example of a Pelton wheel with a single bucket here that we have the jet velocity at the exit of the nozzle before hitting the bucket. Here we have the bucket here, and then the nozzle spray or came at a speed of C1 at the inlet. So here we have the inlet region, and at the 2 is the outlet region. So that we have the jet velocity of C1 hitting the bucket, and then it creates a rotations of the bucket itself, and the bucket rotates at speed of u. And then by subtracting the jet velocity with u, c1 minus u, we have the relative velocity at the inlet, or w1. And also as the jet moves through the curves of the bucket, it creates an angle of alpha through this plane. So we have alpha at this plane, and as a result we have relative velocity of w2 and absolute velocity of c2 at the outlet. One thing that we have to keep in mind, that the speed of the bucket, or u, remains identical or constant throughout the Pelton wheel. So u1 equal u2 equal u. And now let's talk about the Euler equations for the Kaplan turbine, or sorry, for the Pelton wheel. That we know that is equal to work per mass flow rate equal to E, or the energy equations, or the Euler head, that is equal to U1 multiplied with Cx1 minus U2 multiplied with Cx2. Now that we know that U is constant, then there's no need to put 1 and 2 here. And then another assumptions that we have to make, that Cx2 has a negative value in our x direction, so that we can recreate these equations as E is equal U multiplied with U plus W1 plus W2 cosinus of 180 minus alpha minus U. So 180 minus alpha is the angle here. So this is 180 minus alpha, 180 degrees minus alpha. Now, another assumptions that we need to make, that by assuming that there is no energy losses due to frictions between the fluids and the bucket here, it is safe to assume that the relative velocity, or W1, is constant throughout the buckets, and it's W1 equal to W2. And then another thing that we can assume based on the first assumptions is that W1 is equal to C1 minus U, and also cosinus of 180 degrees minus alpha can be equal to minus minus of cosinus alpha. And then with these three assumptions, we can rewrite these equations as E equal to U multiply with U plus C1 minus U from here, from W1 here. We replace it with this, and then we also have that plus the W2 contents, and we know that W2 is equal to W1. Then we can write it down as minus C1 minus U multiply with, so I can write it down here, cosinus of alpha minus U. So, or in a shorter way, or in a simpler way, we can write it down as U multiply with C1 minus U times 1 minus cosinus of alpha divided by gravity. So this is the final form of Euler equations for a Pelton wheel. In a case of maximum flow conditions, or where dE per du is equal to 0, where the Euler does not change over the velocity of the bucket, we can write down the equations for the E max as conditions where C1 is equal to U times 2, or C1 is equal to times U, and then we will have from here that U is equal to C1 divided by 2, and then our E max equations will be, we replace U here with C1 per 2, we will have C1 to the power of 2 multiply with 1 minus cosinus of alpha divided by 4g. This is for the maximum Euler hat equation. So this is 4 times gravity. Previously, we assumed that there is no frictions between the jet or the fluids with the bucket, so that we assume that W1 is equal to W2, or the relative velocity remains constant between the inlet and the outlet of the buckets. But in the real conditions, the frictions exist, therefore we cannot assume that W1 is equal to W2. There's a frictions, and then it will cause a ratio between W1 and W2, and then we know this ratio as K, or the relative velocity ratio between inlet and outlet. Therefore, this will cause change in the Euler equations, and then we will have the actual Euler equations is E equal to U multiply with C1 minus U multiply with 1 minus K, here the ratio, multiply with cosinus of alpha, and we divide it all with gravity. And then this will cause us the first efficiency that we need to deal with, that called as the hydraulic efficiency, or it's simply and H, that is equal to the power output divided by the available jet power. Or in a simple way, or mathematically, we can write down the hydraulic efficiency as Euler head divided by C1 to the power of 2 divided by 2 times gravity.